Let's first talk about this. We've got a conducting sphere inside a conducting shell. Inner sphere has a charge Q, outer shell has a charge negative 3Q. Okay, very easy is inside this conductor, the E field is going to be 0. Okay, the E field anywhere inside the body of a conductor is going to be 0. So also here, between B and C, the E field is going to be 0. Now, if we think of Gauss's law, boom, 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 if I draw an imaginary surface here, the E field is only going to be a function of that internal charge, okay? So the E field is just going to be, we can just use K, Q over R squared for a point charge. So that's also easy. Then outside here, again, Gaussian surface, we can view this whole thing as a point charge of Q plus negative 3Q is negative 2Q. So the E field will be negative K2Q over R squared. Because again, a point charge, the E field is KQ over R squared. So the charge of this one, the charge is negative 2 capital Q. Okay, so there we are. That's not too bad. So 0 up to A, and there's no E field inside that. Then it hops up and it goes down like this. Never goes to 0. Okay, and then 0 here. Then if we look at that, that's twice the charge, but it's negative. So it's actually going to be a bigger, probably a little bit bigger than that, and it's going to go down like that. Okay, now this is a very interesting question. What is the E field between B and C? What does this imply about Q enclosed? What I'm going to do is I'm going to draw an enlarged portion of this. Okay, so here's my plus Q right there. Then I've got the shell on the outside. Well, the E field here is 0. That means Q enclosed has to be 0. Well, that's a little weird because this is negative 3Q. So what actually happens is for the E field to be 0, this has to have a positive charge. In fact, the total inside this conductor, in other words, inside the inner shell, the inner part of the shell and that, has to add up to 0. So we must have, I'm sorry, I put it as a positive. It's negative. We must have a negative charge accumulating on there to make 0 total charge in there. And so that charge on that inner surface is going to be negative Q. Okay, that E field being 0 in a conductor means that the total charge inside has to be 0. Therefore, negative charges will move down here to the point where it makes it negative Q on the inside. But no charge has left this negative 3Q. So negative 3Q is the total. So the Q, I'll just write it as Q outer plus negative Q has to still add up to negative 3Q. What does that mean? Add Q to both sides. That means the charge here on the outside surface is negative 2Q. So if we didn't have that charge in the middle, that negative 3Q would all be around the outside, okay? But when we put that positive Q in there, it attracts some of those negative charges, and they will keep moving until there's no E field in there, okay? If there were an E field in here, it would keep pulling charges, but no. It's 0 E field. So that means there's this division, the separation of charges. No charge in the bulk, but negative 2Q on the outside, negative Q on the inside still adds up to negative 3Q, but allows us to have that 0 E field in the middle. Okay, this is the same thing. We know the situation here. They're both still conducting. Very important to always look at conducting or non-conducting. Net charge of the sphere is plus 2Q. So I'm going to draw that same thing. This just ends up being, we can do this almost by inspection. 0 there and there. Here, K times 2Q over R squared. Outside here, 2Q plus negative Q is just Q. So outside it's KQ over R squared. So we can do that almost by inspection, but that's not the interesting part. The interesting part is looking at, again, there's the shell, there's this inner one. This is 2Q. We know this E is 0, So the charge enclosed has to be 0. That means the charge along this inner surface of the shell has to be negative 2q. Well, the total has to be negative q. So negative q equals q outer. I'll make it a little q outer plus negative 2q. Add 2q to both sides. That means out here, there must be q on the surface. Okay? So okay, negative 2q plus q is negative q. Check. The E field is 0, therefore the total inside has to be 0. Then there's a question here. If I connect the outer shell to ground, boom, 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 and then remove the ground, state E as a function of the distance r. Well, if you connect it to ground, this q from the outer will, actually what's going to happen is a negative charge is going to go up there to balance it out. But you can think of the q getting grounded, basically going to 0 potential. Then we remove it. That's gone. But you still have to have that negative 2q. You still have to have that negative 2q to have an E field of 0. Again, when we remove this, right, what we've done is we've removed that outer charge, but it doesn't do anything to that inner charge because this E field in steady state, meaning after it's been connected for a while, or in this case disconnected, has to be 0. So this will still be negative 2q on there. Okay? Now we get to just densities. Conducting spherical metal ball has a radius of 4 meters. That's gigantic. And surface charge density of 5 coulombs per meter squared. What's the surface area of the ball? The surface area of the ball, well, we know Q equals, Q total equals, I'm sorry, why am I even jumping to that? I'm getting one step ahead. Surface area of the ball is 4 pi r squared. So that ends up being 1664 pi. I don't have my calculator out right now, so I'm not going to worry about this. You can plug it in. What's the charge in the ball? Well, sigma is the charge per unit area. So sigma equals Q over 64 pi. So if we multiply 5 by that, we get 320 pi equals Q. That's a lot of charge. E field 2 meters from the center, it's inside the conductor, 0. 6 meters from the center, it's K times the charge, 320 pi, divided by 6 squared. So let's check. 64 pi, yeah, that comes out to 201. Okay, 320 pi, yeah, that comes out to 1005. And then if you evaluate this whole thing, you should get 2.5 times 10 to the 11th newtons per coulomb. Now let's come up here. This is a much more interesting, much more difficult problem. Okay, R greater than R, no problem. E field equals KQ over R squared, little r squared. So it ends up being K times 3 over R squared. Very easy. Outside here, we can treat it as a point charge if it's symmetrically distributed. Now, R less than R, we have to figure the Q enclosed, okay, kind of Gauss's law, right? So we have to figure out how much Q is in there. The Q out here will not affect it. Now, it is an insulator, so we're talking about uniform charge density. The charge density is the same everywhere, okay? So first thing we should do, we say the charge density of the whole thing is Q over, in fact, I'm going to do this as a general expression. It's going to be Q over 4 for the volume, 4/3 pi r cubed. Okay? Now, I'm going to say that rho prime is the same density. Okay? So we could say the Q prime, in other words, the Q in here, is going to be this density times the new volume. We could put it up as a proportion. Q prime over V prime is going to be this new, I'll call it R prime cubed. Okay, see how that works? So if we evaluate it this way, we're going to be canceling out some things. Either way we do it, if we do, let me just do this way because it's less obvious on this one. Q over 4/3 pi R cubed times my new volume, which is 4/3 pi of my smaller I, R cubed. And you can see, boom, boom, that goes away. So my new Q is Q times new R prime cubed over R cubed. And again, we're trying to find that there. I'm just going to write that as little r cubed. Little r cubed over r cubed. Okay? So now we've got the charge inside. And the E field will just be KQ over little r squared. Okay, E equals KQ over little r squared. And this Q is, and I really should just put it as little q here. K little q over little r squared. But we know what that is. It's K times Q r cubed over r cubed over little r squared. Those cancel. And we end up with K Q R over R cubed. It goes up linearly, which you might remember from when we did gravitation. The G field goes up linearly. Okay, so there is our E field at R less than R. So we got to do a little fussing with that. So again, first of all, find Q inside R, little r, and then E equals KQ over R squared. It's a little more tricky when we get to potential, okay, in the next unit. Okay, now we have a non-uniformly charged insulating sphere. Okay, R greater than A, we have to find the total Q. For R less than A, we have to find the Q inside whatever that R is. So let's start with that. Let's start with that. So E field, the E inside, the Q inside, let me call it Q prime maybe, at R. So we're going to solve this first, R less than A. So what we have to do is add up all the mass. It's the integral of all the mass, all the dq's, okay? And this depends on R. So what we're going to be doing is adding all the little shells. So the charge is going to be the dq is going to be the charge density rho 0 R over A squared times the dV of each of the shells. And we're going to be going out from 0 out to R, little r. Okay? Well, this dV, we're not integrating over volume, we're integrating over radius of these shells. So we really need to reevaluate that. Rho 0 R over A squared. The volume is going to be the shell area times the thickness of that shell, dr. Okay, now we've got everything where we want it. This is our integrating variable. Let's get our constants out. Rho 0, 4 pi over A squared. Integral from 0 to R of R to the 4th dr. That ends up being rho 0, 4 pi over A squared, R to the 5th over 5. Okay, so that is our total charge inside that circle. And the E field just ends up being K times that Q, for rho 0, 4 pi, R to the 5th, A squared times 5, divided by R cubed. So, R squared. So, in other words, this is the charge, KQ over R squared. Some of those R's cancel. Let's pull some 4 pi K rho 0 r cubed over a squared times 5a squared. Let's put the 5 out front. Okay? So a little ugly, but the integration, again, we're trying to find that total charge inside, because if we have the total charge inside, we can treat it as a point charge, and then we can find the E from KQ over R squared. So Q prime is the sum of all the charges of these little shells, okay, because each little shell has a different density because it's at a different distance from the center. So we really just keep reevaluating. Q equals density times the volume. Density, we wrote what the volume of that little dV of the shell is. Then we just start rearranging and integrating. Now, for the whole thing, anywhere out here, it's going to be that total Q. Well, the total Q is just going to be this rho 0 4 pi r fifth over 5a squared evaluated at r, whatever our r is, which we're calling a. That ends up being rho 0 4 pi a to the fifth over 5a squared. So this ends up being a cubed. So the Q total is rho 0 4 pi a cubed over 5. E outside is going to be rho 4 pi a cubed over 5 is the Q, but we multiply that by k and divide by r squared. That's not a now. That's some variable out here. So we're saying anywhere outside, we need to know where this is. And we can see k times whatever that charge is divided by r squared. So it's going to get smaller and smaller. Okay. If you look in here, this is kind of interesting. This goes up with r. Okay. In other words, as you go out, that density goes up, the area goes up, so you end up having some other dimensions that cancel out that r on the bottom here. So you end up with r cubed. I pointed to the wrong thing. So you end up with r cubed in the E. That's really interesting to me, at least. So in other words, that E field up to A will go up, and then it'll go down according to 1 over r squared. In fact, it'll go down more gradually than it went up. Okay, insulating sphere with uniform plus Q in the middle. Oh my goodness. Neutral conducting shell outside. Find E in all regions. Okay, so neutral conducting shell. Now we know E field here is 0. Let's start with the easy one. And we know out here, I'll just put an arrow there, E is going to be treated as point charges, neutral Q, K, Q over R squared, easy. And we know in here, it's E equals KQ over R squared, okay? So it's the exact same thing. So this and this are the same just because this is neutral. In here, the E field has to be 0. So honestly, what's going to happen is if the E field's 0 there, you must have a negative Q charge on the inside and a positive Q to make it neutral on the outside. Okay? Again, not really necessary, but it's important to eventually know this. Okay, now inside that, we're just doing what we did before. My new Q, I'll call it little q. If we figure out the density or we figure out what we're going to end up with is Q times the proportions little r cubed over a cubed. Okay, and I'd refer you to earlier slides to show that. I mean, we don't have to really do that all over again. You can find the density of this and multiply it by 4 pi little r cubed. And when you cancel everything out, you do the density times that, you end up with this. Okay, so then this just ends up being E equals K Q R cubed over A cubed divided by, there's the charge, KQ over R squared. So you end up with KQR over A cubed. Okay? If I connect the outer shell to ground and then remove the ground, well, what's going to happen is, again, the E field, let's connect this to ground. Okay, the E field here, this has to be negative Q for the E field to be 0 there, right? But that positive Q will get removed as a way of thinking of it, okay? So then I do that, the positive Q gets eliminated. I then remove the ground, and this has a total charge of negative Q, and then it ends up being, anywhere in here, it's the same E field as it was before. So in other words, this is true inside, this is true outside it, this is still 0. Outside the whole thing, look, the total charge inside there is 0. So the E way outside, R greater than C, ends up being 0. Okay. Oh, now we get into the hard stuff here. Insulating cylinder. Oh my gosh. Insulating cylinder in the middle. Okay. Uniform charge density, E in all regions. Okay. So let's do really quickly. Let's do our Gauss's law. Okay. And what we have is a length L, and Gauss's law says that the sum of E dot dAs equals Q enclosed over epsilon 0. And the lids, there's 0 E field, right? The ends of it, there's 0 E field because the E fields are pointing out like this in all directions. So it's always perpendicular. The dot product means that goes away. No flux through the lids. So what really happens is the E at a given radius, at a given distance R here, ends up being constant, and so we have the sum of the dAs ends up being the area of that tube, which is 2 pi r times L. The Q enclosed is the linear charge density times L over epsilon 0. The L's cancel, and we end up with E equals lambda over 2 pi r epsilon 0, which ends up being 2k lambda over over r, not over epsilon 0. Okay, so that's the E field for a conducting rod, cylinder, whatever you want to say. Okay, so we have an insulating cylinder in the middle, uniform charge density. Oh my gosh! So now we got to figure out. Well, let's just do this: 2k lambda over r. Let's do the easy ones. E outside. E. I'm going to write it up here. E greater than R greater than C is going to be this total charge of a cylinder, which is negative 2Q plus Q. And I'm just going to plug this in here. Okay, Q per unit length. So Q per unit length, that means the lambda is Q over L. I'm sorry, negative Q over L. Negative 2Q plus Q is negative Q. Divided by L gives me the lambda. So the E is going to be 2 pi times negative Q over L divided by R. So that's way outside, okay? Between B and C, it is a conducting shell. So B less than R less than C, E equals 0. Okay? B between A and B, I keep saying this wrong, R and B, we just treat it as the internal cylinder charge. So it ends up being the lambda. Lambda is negative 2Q over L. Okay, and then we just use our equation. E equals 2K times negative 2Q over L divided by R. So those are the easy ones. The hard one is insulating cylinder. Insulating cylinder. And then let's just, before I go too fast, so in other words, for a cylinder or a rod or a wire, okay, outside that, the E field is 2K lambda over R. So I could apply that here, this way outside, and I could apply that here, between the two. This is easy because it's in a conductor. So now what I have to do, uniform charge density, I now have to find the how much charge when we're inside this. Okay, so in other words, we're looking at a radius in here, okay, little r, that's less than a. I have to find out how much charge, or really what the charge density is, but let's start with how much charge. What's the Q at a less than r? R less than a. I keep getting this backwards. That's the question we really need to ask. Because if we have that, we could do the charge density, and then we could plug it into this equation. Okay, so the density of this is going to be, of the whole thing, is negative Q, 2Q, that's the charge, but divided by the volume. Volume is just going to be pi r squared, which is pi a squared for the whole thing, times L. Okay, so there's my density. Okay, and we can say it's got the same density. Again, you can do this as proportions. So my new Q prime, little q, divided by my smaller volume, which is 4r squared L. Okay, and the L's cancel there, and the 4's cancel there. And so our Q prime ends up being negative 2q r squared over a squared. Okay, so it's really the proportion of those radii squared. Okay, now we got the Q prime, and now we can just use this in this equation. Okay, so the Q prime is this. The lambda, we need the lambda, is going to be negative 2q r squared over a squared. And then per unit length, it's going to be like that. So our E field finally is 2k lambda, we'll put LA squared there on the bottom, divided by r. And the r's, one of the r's cancel, you get negative 4kq r over a squared L. It's a lot, but you're trying to find how much charge is inside that smaller radius, it's smaller cylinder there. Okay.